Okay. Yeah, we already learned this terminology last week, and there is another terminology to indicate the graph. Okay. So, for example, we can have the terminology about hat. So, what is hat? It is a sequence of alternating vertices and edges. Okay, so, what is vertice? This is vertice. And what is edges? So, this is edges. So, a path, it begins with a vertex and it ends with a vertex. Its edge is preceded and followed by its endpoint. So we can have a simple path. Simple path means path such that all vertices and edges are distinct. You know, distinct. It means unique. There will be no repetition. Okay? No repetition. So for example, P1. P1, it is a simple path. So we start from V and then it goes via the XP, it goes to X and via X and then it goes to Z. So this is a simple path. It is a simple path. What about the other path? T2. T2, it is a path, but it is not simple. So if you look at this one, U via Z to W, and then it goes to E, goes to X, via G goes to Y, via F goes to W, and then via D goes to V, like this one. Okay. So this is hat, but this is not simple because when we call this is simple, it means all the vertices and edges should be distinct. Meanwhile, W and W. So it is repeated. So this is repetition. Because it is repetition, so this is a pair, but it is not simple. It is not simple. Because there are, yeah, we visited W two times. So a simple path should have distinct edges and distinct vertices. We have another definition, we call it cycle. Cycle is a circular sequence of alternating vertices and edges. And then its edge is preceded and followed by its endpoints. For example, we have a simple cycle. So it means this is a cycle that its vertices and edges are distinct. Now, you can see cycle C1. Cycle C1, it starts from P and then goes to X via B, goes to Y via G, goes to W via F, goes to U via Z, and then goes back to V via A. So if you look at this one, so this is a symbol to represent that it goes back to V. So it goes back to V. So it is a cycle because this is the circular. Okay, when we start from V and then we goes back to V. So this is a cycle. And a simple cycle is a cycle such that all vertices and edges are distinct. So this is distinct, except the last vertex. C2. C2 is a cycle, but it is not simple. Why? If you look at this one, it starts from U. It starts from U. So we go to W via C, and it goes to X via E, it goes to Y via G, it goes back to W via F, and then we go to V via D, and then goes back to U. Now, if you see W, there are two times. So this is a cycle which is not simple. There is a property of graph. If you still remember the three properties. Yeah. So we have three properties. We also have the properties for graph. The property of graph, we have n, we have m. So n means the number of vertices and m is the number of edges. So we can calculate the degree, okay, the degree of vertex. The property one, it mentioned that the summation of degree equals to 2m. What's m? It is the number of edges. Okay, now let's see this graph. This graph has 1, 2, 3, 4 vertices. So n equals to 4. What about edges? We have 6. We have 1, 2, 3, 4, 5, and 6. Now, the degree of V equals to 3. Now, it is when we have one vertex, there will be 1, 2, 3 different edges. So that's why the degree is 3. What about this one? We have 1, 2, 3. What about this vertex? We have 1, 2, 3. And this vertex, we have 1, 2, 3. Okay. The summation of degree V, it means if we have 1, 2, 3, 4, it means we will have 3 plus 3 plus 3 plus 3. Okay. 3 in this vertex, 3 in this vertex, 3 in this vertex, 3 in this vertex. Then the summation of the degree V will be 3 plus 3 plus 3 plus 3, and it equals to the 2 multiplied by m. What is m? M is the number of edges. So 2 multiplied by 6 means it is 12. So the proof is its x is counted twice. So this one is counted and this one is counted. The property 2, in an undirected graph. You still remember what is undirected? Undirected. Then there is no direction. If there is no direction. In this case, yeah, this is undirected graph. In an undirected graph with no self loop. What is self loop? A self loop is a graph with an x that is going to its own vertex. So an undirected graph with no self loop and no multiple edges. What is no multiple edges? This is if we have one vertex and we have another vertex. So we have one edges, and if we have another edges like this one, then we call this is multiple edges. Okay. So if it is undirected graph and no self loop and no multiple edges, then we will have this property. M is 6. M is 6 is less than or equal to the n multiplied by n minus 1, which is 3 divided by 2. So 4 multiplied by 3, it is 12 divided by 2. Then 6. 6 is less than 6. So it follows this property. Its vertex has degree at most n minus 1. So this vertex has degree n, and it is 4. So n minus 1, it is 3. N minus 1, it is 3. N minus 1, 3. N minus 1, 3. So if we have this, then we will have this property. Now, what is the bound for a directed graph? If it is undirected, okay, then it goes two ways. Right? If it is a directed graph, it means we have one direction. So what is the bound? So in this case, yeah, we will do with up. We will do up from the undirected, because in undirected we have two directions, but in directed graph we have only one direction. So let's check more with the directed graph later. In graph, it is a collection of vertices and edges. So we model the abstraction as a combination of three data types. We will create vertex, we will create edge, and we will create graph. So our text is a lightweight object that store an arbitrary element provided by the user. So for example, you know about the example about airport code. So we assume it supports a method element. It means I want to know what is the element. If it is about airport, then it is the name of the airport. If it is about bus terminal, then it is the name of the bus terminal, and etc. So this is the method element. An X, it stores an associated object. So we learned from the previous example, we can have a flight number. So flight number from Gimpo to Busan using the Korean Air. Maybe we know KE. KE is the number of the text indicate Korean Air, and maybe there is a number, maybe 005, for example. And this is the flight number from Gimpo to Busan, for example. The travel distance, if it is flight from Gimpo to Busan, there might be a minus. Or cost, so how much cost for the airplane ticket from Gimpo to Busan. So it can be also the information on the S. So it will be retrieved with the element method. In addition, we assume that an add support the following methods. Endpoints. You still remember endpoints? The endpoints means if we have a tuple U and V, so the vertex U is the origin of the X and vertex V is the destination. U is origin and V is destination. So if it is the endpoint, if it is starting from U, then the endpoints will be V. If starting from V, if it is the origin, then U is the destination. If there is no direction, this is a directed graph. If there is no direction, then it means U and V are undirected. Opposite. Opposite means we want to know what is the end point from a vertex V. So if I have vertex V, so I want to know what is the end point from the vertex V. If there is another vertex U, then this is the result. If there is another vertex W, then this is the result. So it returns the other end point. So in the graph ADD, we can have this manner. For example, we can count how many vertex are found. And then we can check the vertices. So it will do the iteration, return an iteration of all vertices of the graph. Edge count. So we can calculate how many edges do we have in the class. And edges. So it is an iteration of all the edges of the graph. Get X U comma V. So I want to know what is the X from U to V if it is axis. If it does not exist, then it will return null or null. For an undirected graph, there is no difference between get X U comma V and get X V comma U. V out equals to 3. So we want to know the degree of a vertex. It returns the number of edges. It returns the number of edges incident to vertex V. So if we have vertex V, then we will calculate how many edges incident to vertex V. This is for undirected graph. For the directed graph, return the number of outgoing. What is outgoing? And if we have V, we will check the direction. This is outgoing. This is incoming. This is outgoing. Out means go out. In, it enters the node. So for a directed graph, return the number of outgoing, respectively incoming edges incident to vertex V as designated by the optional parameter. So if you put this one up equal to true, then it means you only calculate the outgoing. The incoming will not be calculated. But if the out equals to false, out equals to false, then it means you will calculate all possible or all edges from the vertex V. Incident edges V out equals to 2. So we want to do the iteration of all edges incident to vertex V. So in the case of a directed graph, report outgoing edges by default and report incoming edges if the optional parameter is set to false. So if this one out equals to false, then it means I want to know what is the incident edges of V. If it is false, then we will return on. But if it is true, then it will be only the outgoing. It will be only the outgoing. Insert vertex x equals to none. So it means we will create a new vertex. So it will save the information x as the element. Insert x u comma v. So we will create and return a new x from vertex u to vertex v. If we need to put a parameter or if we need to put an element, we put the information here. Remove vertex v, so we will remove the vertex v and remove x, so we will remove x from the graph. So you can see now it becomes more complex because in the graph we have not only one, but we have two kind of data, that is vertex and x to consider. Okay. In the graph, we can have several kind of structure. The first structure, we call it X-list structure. So in the X-list structure, we have the object or the vertex object. The vertex object as an element, and there is a reference to position in vertex sequence. And we have X object, where it is an element, and it considers the origin vertex object and consider the destination of vertex object. And it has reference to position in X sequence. So we will check later the vertex sequence and the X sequence. Now, let's say we have this. In this graph, we have U, V, W, Z. This is the vertices. And then we have E, G, F, and H. This is the edges. Okay. Now, we can make this graph with the X-list structure like this one. So we prepare V and we prepare E. V is a sequence. What is the sequence? We have U, V, W, and Z. For the edges, E, we have E, F, G, and H. Now, we want to make the position, the reference position in the vertex sequence. So this is 1, 2, 3, 4. This is the position in the V. And then E, this is the position 1, 2, 3, 4. And it has the origin and destination. What is this one? So E, it is an X between U and V. So E is an X between U and V. What about F? F is an edge between V and W. F is an edge between F and W. What about G? G is an edge between U and W. G is in between U and W. And X is an edge between W and Z. W and Z. So we can create this kind of edge list structure. We can have adjacency list structure. So adjacency list structure means the incident sequence for its vertex. So it is a sequence of references to edge objects of incident edges. So the incident edges, it means if we have a vertex, we want to know the incident of the edges. If we have a vertex, we want to know the incident of the edges. If we have a vertex, we want to know the incident of the edges. We will do the augmented edge objects. Augmented. Okay, do you know what does it mean by augmented? It is addition. So we have the addition. Augmented means addition. It is the reference to associated position in incident sequences of n vertices. So if you see this one, we have V. V is a collection of vertex U, V, W, and Z. In the vertex U, we have E and G. Okay. In the vertex U, this is the augmented object. This is the augmented X object. So it contains E and G. It contains E and G. P, this is a vertex, and it contains E and F. E and F. W, it is a vertex, and it contains F, G, and H. F, G, and H. For Z, it contains only one H, which is H. Okay. Because this is adjacency structure data. We can also do the adjacency matrix structure. So the adjacency matrix structure, we will leverage the X list structure, and we will do the augmented vertex objects. Augmented, this is, as we learned before, addition. So the additional vertex objects, we will use integer key or index associated with vertex. And usually we will do with two-dimensional array, adjacency array. The reference to edge object for adjacent vertices and null for non-adjacent vertices. What does it mean? You can see like this one. We indicate U as 0. We indicate V as 1. We indicate W as index 2 and Z as index 3. So if we know from 0 to 0, from U to U, and empty. What about from U to V? V is what? From 0 to 1. Okay, we have an X, which is E. So we put E in this from 0 to 2. From 0, which is U, to 2, which is W. So we have G. We put G in this cell and so on. So this is the reference to X object for adjacent vertices. So this vertex and this vertex is adjacent. This vertex and this vertex is adjacent. Null for non-adjacent vertex. So this is nothing. Okay, so we call this is null. In the old-fashioned, version, we just put 0 for no X and 1 for X. So you can also do like that one. If you have 0, 1, 2, 3, 0, 1, 2, 3 to indicate each of the vertex. So this is 1, 1, 1, 1, 1, 1, 1, 1. And then the other is 0, 0, 0, 0, 0, 0, 0, 0. It is to indicate that we have a connection between 0 and 1. We have connection between 0 and 2. But we have no connection between 0 and 3. No connection, it is 0. So we need to calculate the performance. There are three kinds of data structure. You can use X list structure, or you can use adjacency list structure, or you can use adjacency metric structure. Let's say you have n vertices and m edges. So we assume there is no parallel edges and we assume no self loop. In the space, we will need n plus m for edge list. N means the number of vertices, m is the number of edges. For adjacency list, we need the space n plus m. But for the adjacency matrix, we need n power of 2. What does it mean? N power of 2. So if we have 14, if we have 4 vertex, we have 4 vertices, 0, 1, 2, 3, 0, 1, 2, 3. So we need to have 16 spaces because the n is 4. N power of 2 means 4 power of 2. It means we have 16. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 spaces. The incident edges means we will check how many times we will find the incident edges of V. So while using the edge list, we have m times. When we use the adjacency list, we just have a degree of V. If we use the adjacency matrix, we have n times. If we want to check whether they are adjacent or not, V and W. So the edge list structure will need m times for the worst case. The adjacency list will need the degree V, comma degree W, and we will check the minimum. For the adjacency list, it is 1. When you want to insert vertex, you need 1 time for the edge list, you need 1 time for the adjacency list, but for the adjacency matrix, you need n power of 2. So it means if you need 1 more vertex here, you need to input another cell in the new row, which is 4, and you need to input also another row for the column 4. And it means it will consume in the worst case n power of 2. Insert X. When you want to insert an X, it will take 1 time this also one time and this also one time. When you remove the vertex, you need m times. In this case, you need the degree of v, and this will need n out of 2. If you remove the x, so it will be only 1, 1, and 1. So from this one, what can you get? The most important thing in making your graph is the vertex. When you remove the vertex, it goes up for the computation time. When you want to check the vertex whether it has incident edges, it also takes more time than only the insert. And when you consider only the edges, if you consider the edges like this one, all of them are one. When you consider the edges, all of them are one. So consideration on vertex will be important for creating a graph. So in the Python, so we can have a variant of adjacency map. Adjacency map. If you still remember when you have the map, so we can use also map to represent this adjacency. For its vertex v, we can use Python dictionary. The dictionary is a kind of map. It is to represent the secondary incident map, LV. So the list V is replaced by top level dictionary D that maps its vertex V to its incident map LV. So if you still remember, we can have the K V. So K, it can be represented by the vertex, and V is a list of edges. So a vertex does not need to explicitly maintain a reference to its position D, because it can be determined O1 expected time. So running time found for the adjacency list graph ADT given above become the expected bound. So if we use the adjacency list with this A, B, so it will be the best option for creating the graph using adjacency map. So this is the vertex class. If you, I will give you the code later. So the class vertex means we have the element, and then we will construct the element, and we want to check what is the element, and we want to give an ID to the vertex. We create another class, we call it X. So here we define what is the origin, what is the destination, and what is the element. So we have U and V and X. It means this is the origin, this is the destination, and this is the element. We have the endpoints. So it is to indicate what is the origin and what is the destination. If I want to check the opposite, V. So it means I need to know if V is the destination, then I want to know the origin. Or if V is the origin, then I want to know the destination. So this is the code. And I want to check the element, and I want to give an ID. So I can use the hash to make ID for games. And you can have a class on graph. So the class graph means I want to create whether the graph is directed or not. Directed graph means the graph has direction. If the directed equals to false, then it means we have no direction. And then we need to set outgoing and incoming. So if there is a direction, means this is outgoing, and here it is incoming. We need to check whether it is directed or not. So if it is directed, then yeah, we need to check whether the incoming is not self-outgoing. So the incoming is not self-outgoing. Okay? So if there is no self loop, then it is directed. You can check how many vertex do you have, and then you can do the looping according to the keys. You can check how many edge count do you have, and you can also do the looping using the function edges. So this is the function that I mentioned before. We can get the degree. So this is the degree of u comma v, and we can get the degree if it is true for the outgoing or false. We can get the incident edges. We can insert vertex. We can insert x, and yeah, this are all the function for the graph. Okay. Okay, I will stop here. So next Wednesday, I will continue with another algorithm or what?